Again, I wanted to do a video for this content for today because it's quite a complicated section of the specification. So we're going to continue with angular motion today, looking at the relationship between moment of inertia and angular velocity, and linking that to the conservation of angular momentum and the angular analogue of Newton's first law. And we're going to have a look at the graphs that represent these. So here is the content that we're covering today. So generating angular momentum, we already know how it's generated. Consider this statement: the rate of change in angular momentum is directly proportional to the size of the eccentric force applied and takes place in the same direction as the eccentric force applied. That should sound familiar to you. What does that sound like? So obviously that's really similar to Newton's second law of motion, acceleration. So as revision, acceleration, N2, the rate of change in momentum of a body, or the acceleration of a body, is proportional to the force, the size of the force, and acts in the same direction as the force applied. And this is an example of the angular version of that. So the rate of change in angular momentum, rather than just momentum, is directly proportional to the size of the eccentric force, rather than the force applied, and takes place in the same direction as the eccentric force applied, or force applied. So all of Newton's laws have an angular version, and they are known as the angular analogue. And that's important because they could use that word in an exam, angular analogue. It's on the specification. It just means the angular version of Newton's laws. And it's how we're going to apply Newton's laws, the laws that we learned last year, we can apply to linear motion. We need to use the angular analogue of Newton's laws when we're looking at angular motion. So the only one of Newton's angular analogues that you actually need to know is Newton's first law. So we know that Newton's first law, a body will continue to in a state of rest or constant velocity until acted upon by an external or unbalanced force. And this is Newton's angular analogue of that first law. So a rotating body, this time rather than a body, will continue to turn about its axis of rotation rather than remain at rest or a constant velocity, with constant angular momentum, unless it's acted upon by an eccentric force or external torque. So what do we mean by that? This gymnast is going to continue to rotate. So a rotating body, the gymnast, will continue to turn about its axis of rotation, in this case the transverse axis, with a constant angular momentum. Her angular momentum will not change throughout the whole of the somersault until an eccentric force or external torque is applied, until she hits the floor. So the main thing to take away from this is this idea of the constant angular momentum. Her momentum, according to Newton's angular analogue of the first law, this somersault, this gymnast will have a constant angular momentum until she hits the floor. Her momentum, her angular momentum, cannot and does not change while she's in the air. So the gymnast generates angular momentum on takeoff, and we've looked at that previously, but once she's in the air, she cannot alter her angular momentum. It remains the same. What can she change though while she's in the air? So obviously while she's in the air, she can change her body shape, and we learned last lesson how by coming into this tuck position and distributing a mass closer to the axis of rotation, she's reducing moment of inertia, and therefore she can change her angular velocity, because those two things are closely linked. So once angular momentum has been generated at takeoff, it remains the same then throughout the somersault, or while the body is in the air, until it touches a surface again, in this case the floor. And from that point, it's a product of angular velocity and moment of inertia. So we need the equation here. So angular momentum then, it's a product of moment of inertia and angular velocity. And what that means is it's really similar to our cardiac output, heart rate, and stroke volume, isn't it? Because if moment inertia is high, angular velocity must be low for this to remain the same. If moment of inertia is low, then angular velocity must be high in order for this to remain the same. So at point A here, moment of inertia is high because the gymnast is in a straight position. And if moment of inertia is high, then angular velocity must be low in order for, because those two things combined give us angular momentum. At B, moment of inertia is low due to the tuck position. And if moment of inertia is low, then angular velocity must increase. It must go up in order to maintain angular momentum. So once it's generated, angular momentum cannot change throughout the movement. It will only change until there's an application of an eccentric force according to the angular analogue of Newton's first law. It remains a constant, and the term for that is a conserved quantity. And again, that's really important. So we say that angular momentum is a conserved quantity throughout a jump or a somersault or any time a body is in the air. It's generated at takeoff, and it cannot be changed until it's an external force or an eccentric force or a torque is applied by some other body. And in that way, it's a conserved quantity. It remains the same. So body maintains its angular momentum until acted upon by an eccentric force, such as in this case from the ground. And that we can think of that two ways. Number one, as the gymnast tucks, her angular velocity has to increase, but she's using that, knowing that angular momentum remains the same. If she wants to increase her angular velocity, then she must decrease her moment of inertia and therefore come into the tuck position. If she wants to decrease her angular velocity, she must increase her moment of inertia because angular momentum must remain the same. It has to remain the same. It's a conserved quantity. So I want you to have a think and write 3 short paragraphs. One concerning takeoff, the point at which the angular momentum is generated. One concerning the flight, the execution, and one concerning the landing point. And make sure in each of your paragraphs that you refer to the moment of inertia. And specifically here, her mass can't change, can it? She can control and change her moment of inertia while she's in the air, but she can't do it by changing her mass. She must be doing it by changing the distribution of that mass. Make sure you refer to angular velocity, you refer to angular momentum, and try your best to refer to the axis of rotation too. So pause the video and then we will go through some examples. Okay, so point A, or the point of takeoff. So during takeoff, the gymnast generates angular momentum by generating an eccentric reaction force from the floor through her body. She then begins to rotate about her transverse axis. The distribution of their mass is away from that transverse axis, so moment of inertia is high, and therefore angular velocity is low because moment of inertia is a conserved quantity. This means for the gymnast, if we're applying it to the sporting contest, for the gymnast, it means that she is able to control her takeoff. Okay. Point B. So during the flight, the gymnast now distributes her mass close to the transverse axis by tucking her arms and legs in. This decreases the moment of inertia and therefore increases angular velocity because moment of inertia times angular velocity is angular momentum, and angular momentum is a conserved quantity. It's not going to change. So by decreasing moment of inertia, we must increase angular velocity. This means for this gymnast that they're able to rotate quickly in this somersault. Angular momentum was generated at takeoff and it's conserved therefore at this point because there is no eccentric force at the moment. So point C then. So at point C, the gymnast distributes their mass away from their transverse axes of rotation by coming out again into a straightened position. This increases their moment of inertia and therefore decreases angular velocity. And this means that they're able to control their landing again. As they actually land, impact on the floor applies the eccentric force that removes that conserved quantity of angular momentum that's been maintained for the rest of the somersault, which allows the gymnast to stand at the end of the move. It allows her to stop angular motion. So again, have a go with the skier. So the skier is entering this, what is a forward somersault backwards. So coming up this side, forward somersault, and out at the other side. Try to think about takeoff, flight, and landing, and refer to eccentric force, angular momentum, moment of inertia, angular velocity, and axes of rotation. So hopefully this is exactly the same. At takeoff, there is an eccentric force generated by the skier, which generates angular momentum. That angular momentum is then a conserved quantity, it does not change throughout the whole of the somersault until the skier lands at this landing point. At takeoff, moment of inertia is quite high. They've got the legs, the knees are extended, although they are flexed at the hips, which means the angular velocity must be quite low because angular momentum is moment of inertia times by angular velocity. So if moment of inertia is quite high, then angular velocity is quite low in order to conserve angular momentum. And that means that the skier can control the takeoff. In flight, the skier adopts this tuck position, knees tucked into the chest, which decreases moment of inertia, which means that angular velocity must increase in order to conserve angular momentum. And it means that they complete the somersault quite quickly, obviously rotating about that transverse axis. And then when we come into landing, at this point we touch the floor, which means there's an eccentric force again applied to the skier, which removes the conserved quantity of angular momentum. It allows them to stop rotating and to stand on the snow. Obviously, coming into landing, they've increased the moment of inertia by straightening out the body, which must mean that angular velocity decreases, which allows them to control the landing. So let's consider the snowboarder. We've got a different axis of rotation this time. It's the axis that comes through the front of the body, therefore it's the frontal axis this time. They're doing a side somersault, but they've chosen to do it in a straight position. So why might the snowboarder choose a straight position for this somersault? So I would suggest that they've chosen this straight position because it's worth more points. Moment of inertia is high, and it's high throughout the whole of the jump. Angular momentum is generated on takeoff and remains a conserved quantity, and a moment of inertia is the same throughout, it's high. And that means that throughout the whole of this move, the angular velocity of the snowboarder is low, and that means that it's really hard to get the somersault in the time. So they've chosen the straight position because it's harder and presumably worth more points. So have a go now at stating Newton's first law and then the angular analogue of Newton's first law, and then apply that to each of these snow sports examples. So Newton's first law then, a body will continue in a state of rest or constant velocity unless acted upon by an external or imbalanced force. The angular analogue of Newton's first law, let's go so you can see it. So a rotating body will continue to turn about its axis of rotation with constant angular momentum unless acted upon by an eccentric or external force or torque. So in this example, the snowboarder, we must apply the angular analogue of Newton's first law because we've got rotation, we've got angular momentum here, or angular motion rather than linear motion, so we need the angular analogue. So this body, once the angular momentum is generated, the body will continue to rotate about its transverse axis until it's acted upon by the external force, the external eccentric force from the floor. And in this example, the body will continue to turn about the frontal axis until acted upon by the eccentric force, again on landing from the floor. So we're going to have a go at a few past paper questions now. It's up to you. You can either write out the question and then pause the video and have a go at answering it, or you might want to write out the question and have a look at the answer and listen to me talk it through and then have a go at answering it. So question number 1, explain how angular velocity is controlled by the gymnast during takeoff, flight and landing. This question is worth 6 marks. It's explain. It's going to need some detail here. The controlling of angular velocity should be making you think of moment of inertia and angular momentum as well. So we're going to need to talk about all 3 in this question. So here's the mark scheme. We probably might have started at takeoff, so I would have liked to have seen you structure this answer in 3 sections: takeoff, flight and landing. The question is about the 3 phases. We need to make sure we get the 3 phases in. So probably would have started by saying at takeoff, the gymnast generates angular momentum from the floor by applying an external eccentric force. And then I probably would have gone on to state that angular momentum will remain then a conserved quantity throughout the backwards somersault. And that is due to the angular analogue of Newton's first law, and then we could have stated that. So a body will continue to rotate about its axis with constant angular momentum unless acted upon by an external torque or an eccentric force. And then we would have been able to get in this relationship between moment of inertia and angular velocity. So at takeoff, moment of inertia is high because the body is extended. And because moment of inertia times angular velocity equals angular momentum, and angular momentum is a conserved quantity, if moment of inertia is high, then angular velocity must be low. During the flight, moment of inertia is then reduced when we're in this tuck shape, which means that angular velocity must then increase in order to maintain angular momentum. And on landing, moment of inertia is increased as the body again is extended, ready to land, which must mean that angular velocity decreases in order to maintain that angular momentum. And that's done there to prevent over-rotation or to control that landing, as we said previously. So there are a lot of possible marks there, but you'll see that you needed to get 3 AO1 and 3 AO2 to get the 6 marks. So you had to pick up these 3 marks for all 6 marks. And it meant that this question needed to sort of say in your brain, explain angular velocity. Well, if I'm going to explain angular velocity, I need to mention moment of inertia and I need to mention angular momentum, and I'm going to need to talk about how angular momentum is a conserved quantity and the angular analogue of Newton's first law. Okay, so all of this was a really complex question that needed to spot lots of different theory knowledge in order to score 6 out of 6. Okay, a bit of an easier question perhaps now. Explain using the angular analogue of Newton's first law of motion the concept of conservation of angular momentum. So again, for this one, we're going to need to be able to define Newton's first law, the angular analogue of Newton's first law, but we need to say what that means about the conservation of angular momentum. So this was a generous mark scheme because you got 2 marks for being able to define the angular analogue of Newton's first law. So a body will continue to rotate about its axis of rotation with constant angular momentum until acted upon by an eccentric force or a torque. That was 2 marks potentially. So then you probably have gone on to then say that this means that once in flight, once angular momentum has been generated, a change in moment of inertia has to mean a change in angular velocity, because angular momentum is moment of inertia times by angular velocity. So if we're in flight, angular momentum has to remain constant. It will not change until acted upon by an external force, and therefore if anything does change, if moment of inertia does change throughout the flight, angular velocity must then therefore change during the flight. And you may have gone on to then use an example to say like a performer might change their shape, such as a tuck position, to change moment of inertia and therefore angular velocity in order to conserve angular momentum. Okay, final question. So we haven't seen this graph yet. This is the graph that represents this relationship that we've been talking about between angular momentum, moment of inertia, and angular velocity. So the graph shows the relationship between moment of inertia, angular velocity, and angular momentum during the performance of a tucked somersault. So angular momentum is remaining the same. It's a conserved quantity. This person must have taken off at this point because angular momentum has been generated and it's high, and it remains constant throughout the whole of the tucked somersault. And we know at the start of the tucked somersault, moment of inertia is low because the body is straight, and therefore moment of inertia is high because the body is moment of inertia is high because the body is straight, which means that angular velocity must be low in order to conserve angular momentum. At the tucked point, moment of inertia is low because the mass of the body is towards the axis of rotation, distributed towards the axis of rotation, which means angular velocity must be high in order to keep this line where it is. And towards the very end of the jump, moment of inertia is high again as we untuck the body, which means angular velocity must decrease in order to keep this the same. If this goes up, this has to come down. If this comes down, this has to come up to keep this the same. Exactly the same relationship as cardiac output, stroke volume, and heart rate. So explain the shape of the graph with reference to a tucked somersault from A to B. We're only looking for this part of the graph, an explanation of this part of the graph. Okay, so at A, moment of inertia is low, which means that angular velocity is high. So moment of inertia is low because the performer is in a tucked position. You had to be talking about with reference to the tucked somersault. So you had to talk about the tucked somersault in your answer. So to say that at A, the moment of inertia is low because they're in a tucked position and therefore the angular velocity is high. From A to B, moment of inertia is decreasing moment of inertia is increasing because the performer is straightening out their body, moving their mass away from the axis of rotation, which means that angular velocity has to decrease because this body is now increasing its resistance to motion. It's increasing its moment of inertia because they're moving their body away from the axis of rotation. Angular momentum is conserved throughout this part of the graph from A to B because as moment of inertia increases, angular velocity decreases in order to conserve angular momentum. And we know that that has to happen because we know the equation. We know that angular momentum is equal to moment of inertia times by angular velocity. Okay, so that's it. You might want to go through the slides again. Just like last lesson, I've posted the slides as well as the video, so you can go back and look at some of the slides again, re-listen to part of the video, try and answer the questions again. Make sure that at the end of this, before you move on, you understand the relationship between moment of inertia and angular velocity. As one goes up, the other must come down. And that you understand this conservation of angular momentum, that once it's produced, it remains the same. It's a conserved quantity until the application of an eccentric force, and we know that due to the angular analogue of Newton's first law of motion. You need to know that angular analogue of Newton's first law of motion. And then interpreting the graph, and the graph is this graph where we see angular momentum conserved, moment of inertia. If moment of inertia is high, angular velocity is low. If angular velocity is low, moment of inertia is high, in order to conserve that angular momentum. And that's all for this lesson.